right, this is on Voltaic cells. This is the solution. If you don't feel like you need the entire worked out solution to this, then go to SharePoint and find the document for it. But otherwise, let's work through this. The battery that I asked you to make is, it says to design a battery using magnesium and lead and their corresponding ion solutions. So a solution of magnesium ion and lead 2+. That's not the only charge for lead. There's other ones, but if you look, and in fact, you probably should pause the video here in a moment and open up your book to page 533 and look at that table 17.1. You could pause it now. Go get your book. But this table, the only one we can really find is lead 2+ on there, so that's going to be a good ion thing. So if we're going to design a battery, first of all, the metals that we're using are magnesium and lead. Those are the electrodes. The electrodes are the metal pieces in there. When we build a battery, the idea of a battery is to take a redox reaction where there's a transfer of electrons and separate the two pieces so that the electrons have to travel over a wire. So here's a wire that I'm going to use to connect my two electrodes. Now, if I was using this electricity, maybe I'd be using it to light up a light bulb or something. I could use the movement of those electrons to power up my light bulb. But it's going to provide us with a voltage. So I'm going to put the magnesium into a magnesium ion solution and the lead into a lead ion solution. And the reason I'm doing that is because I know that lead is not going to react with an ion of itself. Magnesium's not going to react with an ion of itself. So I don't need to worry about side reactions taking place. Now, I never would have just straight magnesium. Perhaps it was a that didn't come out. Magnesium nitrate solution, and let's just say it was a lead nitrate solution. So I've got both the positive and the negative ions in solution. So there's my diagram. I need to figure out what the balanced equation is. And so here's where table 17.1 comes in. I need to have something being oxidized and something being reduced. So when I look at the table, notice that everything in the table is listed as a reduction. So, for example, find these two equations on the table. There's magnesium ion gaining 2 electrons to turn into magnesium, and there's an E0. This is a standard potential, which we can get a voltage from. For the magnesium is negative 2.357 volts, and above it, sorry, I don't have my book open to that page right here, but above it we have lead ion being reduced, turning into lead, and its voltage is negative 0.127 volts. So then there's lots of other stuff above and below these things on the chart. The idea of a battery is, in order for us to get a voltage out of our battery, for it to work, we need to have an oxidation and we need to have a reduction. And when we add those together, we need to get a positive voltage. What that tells me is one of these two reactions needs to be switched to make it an oxidation, because right now they're both gaining electrons, so they're both written as reductions. Since I know I need them to add up to a positive voltage, whichever one I switch, I also have to switch its sign. So as I look at this, if I switch the sign on magnesium to a positive number and add it to what I had for lead, I will get a positive voltage. So that's how I make my decision. So magnesium is going to be reversed. Magnesium is what's going to be oxidized, and its E0 value now becomes positive 2.357 volts. I'm going to leave the lead alone as a reduction. So its E0 value is going to stay the same, and it's going to be negative 0.127 volts. Now, incidentally, I need to write a balanced equation. That's what the second bullet point says, to write a balanced equation. These are my half reactions. The nice thing is these are very simple. There's no oxygens to balance with water, no hydrogens to balance with H+, and the electrons are already balanced, so I don't even have to multiply these by anything. But if I did have to multiply these, I would never multiply the voltage, even if I multiply the reaction. So keep that in mind. So this one can be written right away, the balanced equation. The electrons cancel, so I end up with magnesium plus lead 2 plus, yielding lead and magnesium 2 plus. This is my balanced equation. That's part of the answer. I simply need to add these two values together, so my standard potential for the battery, my voltage for the battery that I can get out of my battery, is 2.230 volts. I simply added these two, and that's the value I get. In order to have a working battery, it always needs to be a positive number. Great. Now, the abbreviation for the battery, your book talks about this, but in terms of the abbreviation, we always write the metal, the oxidation, and then that's divided, and the reduction is listed. And you always list the, like if we look at this equation, the oxidation starts with magnesium going to magnesium 2 plus, so it's magnesium 2 plus, that's the oxidation side. And then on the reduction side, lead 2 plus turns into lead, so lead 2 plus and lead. So that's your abbreviation there. Other things, so I calculated the E naught, I have the abbreviation. Oh, label and define stuff. All right, back up here. Back in the day, you may have remembered anox and red cat. This means at the anode is where oxidation takes place and reduction takes place at the cathode. The cathode and the anode always have to be the electrode, so the metal pieces. There are some exceptions in your book when you don't have a metal piece, and so you can read about those. But since magnesium over here, this is the oxidation, and since lead is the reduction, or the lead 2 plus is being reduced, then the metal electrode where that happens is each. So that makes the magnesium, where oxidation takes place, is the anode, and the lead, the metal piece where reduction takes place, is the cathode. By definition, the cathode is always positive and the anode is always negative. So in our battery, that will be true. What is being oxidized? The magnesium is being oxidized. What is being reduced? The lead 2 plus is the actual thing being reduced. The oxidizing agent, if magnesium is oxidized, then it is also the reducing agent. If lead 2 plus is being reduced, it's also the oxidizing agent. We saw that a little bit in class. Oh, a salt bridge. This battery won't work right at the moment because there's going to be charges building up. Because if magnesium starts breaking down and producing more magnesium ions, we're going to start to develop extra positive charges. And if the lead 2 plus keeps gaining electrons and turning into lead, then we're going to start having extra negative nitrates in there. Notice, you guys, that has absolutely nothing to do with the charge. The charge is simply a label. That's it. So what we need is we need a salt bridge. And a salt bridge is usually has a solution in it. I'll make an example of this being, I don't know, KCl, just as an example, that has this solution in it. Well, if we start producing lots of extra positive ions over here, then in order for a charge not to build up, any negative ions are going to be attracted to that side. And in fact, any negative ions over here will start to be attracted to that side. So what I want you to notice is that anions are attracted toward the anode, which is kind of easy to remember. Why? Because those positive charges are building up. On the flip side over here, if we have lots of negative charges because these are being removed, so there's still lots of negatives, that means that the positive ions in the salt bridge, like K+, are going to be attracted to this side to neutralize the charge. And eventually, even some of the magnesiums might start to travel. So towards the cathode, cations move towards the cathode to help neutralize the charge. So that's the movement of the ions. Now, the movement of the electrons, which is really important, we can see that based on this reaction. The magnesium loses the electrons. The lead 2+ gains them. So the electrons leave the magnesium. They travel across the wire. They don't stop at the lead because the lead doesn't accept them. It's the lead 2+ that accepts them. So it travels all the way until it hits the lead 2+. That's what causes the lead 2+ to turn into the lead. So that's the movement of electrons. And we have to read that movement of electrons from our balanced equation and see who's losing the electrons and who's gaining the electrons to help us to decide. All right, this became a total mess on here. But if you want to see a neat version, just go to SharePoint, and I've got a prettier version of the solution there than this mess. But it basically, I've tried to talk you through all of the different parts and pieces. So good luck, have fun, try another one.